Okay, let's get right into it. Today's explainer dives into a seriously fascinating IGCSE computer science masterclass, and it is specifically designed to help you completely reverse engineer a perfect exam response, and frankly, save your grade. We're stripping away all the textbook fluff here. Instead, we are jumping straight into the exact mechanics of what a Cambridge examiner is actually looking for when you sit down for that Paper 1 exam. Because look, just understanding a concept, that's really only half the battle. Knowing exactly how to structure that understanding onto the page, that is the real secret sauce that separates the average scores from the absolute top bands. So let's look at exactly how things usually go wrong first.
Just take a look at this statement for a second. A switch sends data to all computers on the network to make sure it arrives. Now, if you write this, or honestly, anything remotely close to it in your actual exam, you are getting exactly 0 marks. Nothing. Zilch. It's an incredibly common, really painful learner mistake that just instantly destroys your score on a hardware question. And you might be wondering why. Well, sure, it sounds somewhat logical to a total beginner, but it completely lacks the specific technical precision that Cambridge demands. It actually shows the examiner a fundamental misunderstanding of what a switch truly does in the real world.
Okay, let's dive into this. The source material points out a massive, massive difference in how you can answer this. On one hand, we've got that weak, generalized answer, sends data to all computers. It's just way too vague, but contrast that with the exact wording the examiner is hunting for, connects source and destination directly via specific ports. Do you see the difference there? The top-end answer uses incredibly precise nouns and verbs. It's not just describing some general action, it's literally describing a mechanical networking process. To secure those full marks, we absolutely have to upgrade our vocabulary and our structural understanding of the whole system. But hey, before we can fix that hardware problem, we need a totally bulletproof foundation. The source stresses that this right here is the absolute foundational definition you need to lock in. A computer network is simply a set of devices, which we technically call nodes, connected through communication channels, which we call links, for the specific purpose of sharing resources. That's the whole shebang. A node could be a computer, a printer, really any device that can send or receive data. And those communication channels, those are just the physical wires or the wireless paths that actually tie the whole setup together. Now, you might be asking, why do we even bother setting all these up? Well, the benefits are highly practical, and for you, they're highly testable. First up, file sharing. It gives you immense flexibility with your documents and media. Second, and this is absolutely crucial, networks allow for critical data backups to entirely different computers. It's honestly one of the most important yet somehow most overlooked tasks in any system. And third, peripheral sharing. Because we have networks, you don't have to save a document to a clunky USB drive and bounce between 3 different computers just to print out a single email message. One printer literally serves the whole network. Game changer, right? All right, moving on to Section 1, Transmission Technologies. We're looking at broadcast networks versus point-to-point. So how does data actually move across those links we just talked about? Well, let's start with broadcast networks. I want you to imagine a super crowded room where one person just shouts a message at the top of their lungs so everyone can hear it. That is essentially a broadcast network. It relies on a single communication channel that is shared by absolutely every single machine on the network. A short message goes out and everyone receives it. The glaring issue here, as you can probably guess, is that when everyone tries to shout at the exact same time, you get severe network congestion and a whole lot of data collisions. And here we can see the exact contrast. We have our broadcast model with its shared and honestly often congested channel versus the point-to-point model. The source highlights some absolutely key terminology you need to note here because these are the exact examiner words you need in your arsenal: dedicated bandwidth and low latency. Point-to-point provides a direct, completely uninterrupted method of communication strictly between 2 devices. There is 0 sharing of that specific channel, which drastically cuts down the delay, or what we call the latency of the data transfer. Now, because of that dedicated bandwidth, point-to-point networks have some very specific use cases. They are absolutely incredible for secure connections between specific endpoints, especially when you absolutely cannot have your data intercepted or delayed by other traffic. They're also heavily used to connect remote locations or establish dedicated, super high-speed links within a much larger network infrastructure. But, and this is a big but, they are entirely impractical for massive global networks. I mean, you simply cannot run a dedicated physical wire from your personal laptop to every single other computer on planet Earth. Now, in just a moment, I'm going to show you the hidden examiner clue regarding switches versus hubs that changes a hardware question completely. It's a real game changer. But first, we actually need the framework that makes this clue so obvious. Let's walk through it together.
Okay, this is what the masterclass calls the answer upgrade framework. It's the exact sequence you should run through in your head the second you see a 4 to 6 mark question. Step 1, define the core concept. Step 2, explain the specific network mechanism, like how it actually works behind the scenes. Step 3, apply it to the exact scenario nouns given to you in the exam question. And step 4, translate that entire thing into the precise examiner wording pulled straight from the mark scheme. Visualizing this sequence is exactly how you build an impenetrable, high-level response.
Let's move to Section 2, Network Hardware Components, and see how this builds when applying the framework directly to hubs, switches, and routers. Let's see exactly how this builds when we apply our shiny new framework directly to physical hardware. On paper, and even if they were physically sitting right there on a desk in front of you, a hub and a switch look virtually identical. And this is exactly why so many people get them confused. They both share common features. They both have multiple RJ45 ports for plugging in your Ethernet cables, they both have a power supply, and they both feature those little flashing connection lights. So listen closely. If an exam asks you to compare them, do not, I repeat, do not talk about what they look like. You absolutely must talk about how they handle data.
Okay, step 2 of the framework is the mechanism. And here is the mechanism of a hub. Remember the broadcast model we talked about earlier? Well, a hub operates entirely on that model. A hub blindly broadcasts every single received message to the entire network. It literally doesn't care who the message is actually for. If data comes flowing into port 1, the hub just copies it and blasts it right out of ports 2, 3, 4, 5, and the rest of them. It is essentially an unintelligent device that just causes a ton of unnecessary traffic. All right, the masterclass poses a quick interactive challenge for us here. Let's say a home network needs to connect a LAN to a single internet connection. Okay, based on those highly specific scenario nouns, connecting a local area network to the internet, should they go out and buy a hub, a switch, or a router? Take a second and lock in your answer in your head. Okay, if you thought router, you hit the nail on the head. That's exactly right. The textbook definition of a router is a device used to connect two distinct networks, like your home LAN to the massive internet, and manage all the traffic flowing between them. But here is a super surprising fact for your practical knowledge. Most modern routers you'd buy for a small business or your house, they actually include a built-in switch right inside them. So while they are technically different devices performing very different roles, they're often just bundled together into that same little plastic box sitting on your desk. Pretty cool, right? Just real quick, to actually get connected to any of these devices, your computer obviously needs a network card, and you just need to be aware of the difference between the internal and external options. An internal wireless network card requires physical insertion directly into the motherboard, which means yes, you have to open up the computer case, but the massive perk is it requires absolutely no external cables. Contrast that with an external USB network card, which is just an easy plug-and-play device on the outside of the machine. It's simple, but trust me, it is highly testable. Now, what's really interesting here is that this is where that hidden examiner clue finally clicks perfectly into place. Quote, unlike a hub, a switch connects the source and destination directly by checking the specific system or port. You see, a switch is actually intelligent. When a message comes in, the switch reads the data packet, checks exactly which port the destination device is plugged into, and then sends the data only to that specific port. It essentially creates a temporary, super fast point-to-point connection. And if we keep following our framework, we then have to state the direct consequence of that mechanism. Because the switch checks the port and connects directly, it entirely avoids broadcasting. And by avoiding broadcasting, it completely eliminates all those messy collisions and network ingestion. So the measurable, highly testable advantage here is that a switch dramatically increases the overall speed and efficiency of the network when compared to a hub. That right there, that is your gold medal full marks answer. Think of this breakdown as your perfect mark scheme safe upgrade guide. Whenever the exam throws a compare or evaluate command word at you, this is exactly how you need to structure your logic. Let's recap. Hub. Blindly broadcasts to all, resulting in zero advantages and significantly slower speeds. Switch. Checks the specific port and connects directly, resulting in massively increased speed. Router. Connects the LAN to the internet, allowing multiple devices to share just one connection. This is absolute precision. So a switch manages direct connections perfectly inside your local area network. But man, that raises a really fascinating question. If a switch handles all these direct connections locally just to boost speed, what on earth happens to that data packet the exact millisecond it leaves your LAN, passes through the router, and attempts to travel across a massive, totally chaotic wide area network, the internet itself? Well, I'll tell you this, the rules of transmission completely change. If you found this breakdown of the masterclass valuable today, absolutely make sure to follow along for more explainer content where we take complex topics just like this one and completely reverse engineer them for you. To answer that massive question about what actually happens when your data finally leaves the safety of the land, we have to look at wide area networks. It's an entirely different beast altogether. As you continue to prepare, ask yourself, how in the world does the internet manage to route data securely across the entire globe without just collapsing under its own massive weight? Check out our next explainer on wide area networks to find out exactly how it works.